I presented my research on robust optimization framework that we propose for cancer diagnosis that accounts for prediction errors. In particular, how we can integrate data-driven optimization and machine learning that combines multiple imaging tests into a composite testing protocol that accounts for the errors in the predicted probabilities obtained from statistical models.
The work that I'm presenting on at Informs this year is looking at access in our cities. And this is kind of motivated by the issue of social justice and the idea that there's maybe inequities in access to services between different demographic groups in our cities. So we're looking at access to green space in cities, and we've kind of developed a method that measures access to green space on a citywide scale, and we're kind of looking at potential inequities or disparities in this access between different demographic groups.
The research I'm presenting here at Informs this year is regarding risk prediction models in healthcare. So for instance, an example might be a model which takes in your personal characteristics and some clinical risk factors and predicts maybe you have a 30 or 40% chance of having cancer. And our goal is to figure out, well, what risk level constitutes enough evidence to say that yes, you do have cancer, what level says no, there's not enough, or maybe there's a region in between where we're not really sure and maybe more tests have to be done. So we applied this method, we proposed to answer this question using data-driven optimization methods, and we applied it to concussion data, which is pretty unique in our field.
So Dr. Gaikima and I have been working on improving some of the existing predictive models that predict the power outages when a hurricane landfalls. And so we're looking at a lot of different variables like the climate variables, the wind, geographical variables, population density and things like that. And we realize that there are really a large number of variables that we can include in our model. So we're interested to see if we can find a subset of these variables that are most informative, and so that can hopefully help us with increasing the power of our prediction model.
I work on drug shortages, and shortages have become a really big deal in the past 5 or 6 years or so. Essentially, there are hundreds of drugs that are unavailable at any given time, and shortages last over a year at any given time, and can have an immense cost to our healthcare system. When Hurricane Maria hit Puerto Rico, in addition to the devastation that was caused to the island and the incredible loss of life, we also find that there are a number of pharmaceutical companies that have plants down there. When they don't have electricity, they also can't produce life-saving drugs, which becomes a major issue if we don't have redundancy. And so I work in the space of trying to incentivize pharmaceutical companies to be more resilient so that we can prevent some of these shortages.
The main goal of cardiovascular disease management is to prevent the onset of heart attacks and strokes. So despite the fact that this is a very important disease, it's a major killer in the United States, there's still these open questions about how you should actually be managing the risk for cardiovascular disease. So the problem with using risk as your basis of your treatment guidelines is that there could be misestimations in the risk itself. So you could take the same patient, and depending on which clinical study you look at, there might be different estimates of how that patient, how at risk they are for these major events like heart attacks and strokes. So we're looking at how you can actually resolve those differences and how you can come up with these robust treatment guidelines that are kind of would perform well despite which clinical study you're using in your treatment recommendation.
My research is basically about the prediction of wind farm output. In this research, the objective is to first capture the wind speed characteristics, and second, we try to capture the relationship between wind to power, and finally, we try to quantify the variability of speed and power in a more like integrated way.
So my research is about how we adapt our cities to climate and environmental change. And one of the things that we're doing when we adapt is we risk what's called maladaptation. And so the research that I'm presenting today is looking into whether these hard adaptive measures like seawalls and levees whether they do actually increase or reduce our risk over time. And what we're seeing is that often, because they induce like a false sense of security and encourage development in risky places, we're seeing that our communities become more vulnerable, and that's kind of the questions that we're trying to ask and delve into.
So basically, we're building an algorithm to solve the inventory system, which has a random production capacity. So imagine that because of the insufficient of materials or maintenance, you might not sure how much you can produce in each period. And also the demand is also random. And different with the traditional literature, we don't assume any distribution of demand or capacity. So we need to learn by observing the data and make adaptive policy or adaptive recommendations to the firm how we gonna order in the next period.